Hi, my name is Rich, and my project, which I call StickOS, is an MCU-resident rapid prototyping and education environment for highly integrated MCUs, including Zigbee wireless support. So here's my badge board, and it's running StickOS, and I've got a little paddleball game running on top of that, and we're going to play it. It's a little bit different. It uses the accelerometer to control the paddle, and it's got sound effects, but let's see how I do. You can see I'm moving the paddle there. There, I bounce the ball. I bounce the ball again, I bounce the ball again. This is actually pretty good. So anyway, and then there's the sound effects. This isn't really about paddleball. This is about software development. It's about one of my dreams coming true. One thing that I've dreamed about forever is the mythical computer on a chip. I'm not talking about just a programmable chip here. I'm talking about a real computer on a chip, right? A computer like this is interactive, right? You can log into it, you can program it, you can debug your programs there, you can save your programs. Well, that's what I want from an interactive computer on a chip, and that's what I've got finally from the badge board MCU here. Internal to this MCU is an entire StickOS BASIC programming environment that includes an easy-to-use editor, a line-by-line transparent compiler, an interactive debugger, and a flash file system. So basically I can log in using just a dumb terminal emulator. I can log in via either USB or Zigbee wireless, and I can interact with the computer on a chip. I can program the computer on a chip. The programming environment inside here understands all the peripherals that are built into the computer on a chip. So, it costs me one line of code in order to do things like configure an analog digital converter or a pulse width modulator or a frequency generator or anything like that. One line of code for each one of these kinds of peripherals. I can bind variables, pin variables, to any of the pins on the chip. And I can manipulate those variables just as if they were regular RAM variables, and instead what happens is the pins get manipulated, or the pins get examined if I look at the variables. So basically what I've got is I've got a programming environment that's tightly integrated with the MCU, understands all the capabilities of the MCU, exposes high-level constructs of the MCU, and then allows me as the programmer to just bind together the internal peripherals and the external pins in high-level algorithmic meaningful ways, as opposed to asking me to go and do complex sequences of I/O register manipulation or anything like that. So the goal of the programming environment here is to basically make the programming simple enough for people who don't want to get intimate with their MCUs to still be able to take advantage of all the functionality within the MCU, bind things together in a high-level way, and have everything just work. Anyway, let's go take a look at what a paddleball program looks like real briefly. So we're going to do a whirlwind tour of a basic program. You can see basically here's the badge board. We turn it on, and the program starts to run. We connect up the USB port. Now we can go here and we can hit Control-C, and that's going to stop the program. And you see we just said stop at line 750, and then it's give us a little welcome message. We can actually continue the program, and you'll see the program start again, and then we can stop it again. And we can list the program. You'll see it's 93 lines of code down there. If we look at the beginning of the program, you'll see basically that where we're doing our essentially pin and peripheral configuration. We're binding some variables to some pins for digital output. We're binding, for example, the tilt variable. We're binding it to PTP5, pin PTP5, and we're configuring that pin for analog input. So anytime we examine that variable, we're going to get the number of millivolts on that pin. We've got an audio variable that we're binding to pin PTF2, and we're configuring it for frequency output. Anytime we set that guy to a value, say 1,000, all of a sudden there's going to be a 1,000 hertz tone on that pin. Set it to 0, and the tone turns off. Likewise, we're also configuring a timer to interrupt every 50 millisecond, and we're saying, every 50 millisecond go sub the paddle subroutine. Anyway, so that's basically a super high-level whirlwind tour of some of the functionalities of the basic program, and we'll be right back. So where do you go if you want more information? It's all on the web at www.cpustick.com. It's like a memory stick, but it's a CPU stick, all one word. There's full documentation. There's downloads available for all the different MCUs. There's examples. You can see a toaster oven temperature profile controller that I use to reflow surface mount boards in my house. You can see wireless examples where you can make a remote LED dimmer over Zigbee that takes like 10 lines of code. There's pictures if you want to see any of the boards that I've built. Basically it's all there, and there's if you're an educator and you're interested in trying to get this into a school, you can contact me on the Contact Us link. Anyway, thank you very much.